July 1st, 2025, a telescope in Chile picks up something moving fast, 137,000 miles per hour through space. The asteroid terrestrial impact last alert system, ATLAS, designed to catch rocks that might hit us, but this one's different. 24 hours later, the numbers come back, and every astronomer who sees them stops what they're doing. The trajectory doesn't curve back. It doesn't belong to the sun. It came from somewhere else, out there, between the stars. This is 3I Atlas, the third visitor from beyond our solar system ever confirmed. The first was Oumuamua in 2017, cigar-shaped, dark, gone before we understood it. The second was 2I Borisov in 2019, a comet, red dust, water ice, normal. 3I Atlas is neither. It moves at 58 kilometers per second relative to the sun. That's double Oumuamua's speed, almost double Borisov's. When something moves that fast, gravity can't hold it. It's not orbiting. It's passing through. One visit, then gone forever into the void. The shape of its path. That's what proves it. Every object in our solar system follows an ellipse. Eccentricity below 1, a closed loop, but hyperbolic trajectories. Eccentricity above 1, those don't close. They're escape routes. 3I Atlas has an eccentricity of 6.141. Oumuamua was 1.2. Borisov was 3.4. This thing blows them both away. An eccentricity that high makes the path look almost straight. A rifle shot through the planets. Astronomers traced it backward through 10 million years using data from the Gaia Space Observatory. They checked 93 potential stellar encounters. 62 were significant. None explained where it came from. No star bent its path enough. It just appeared, moving away from the galactic center at 51 kilometers per second. Moving upward through the galactic disk at 18.5 kilometers per second. That vertical velocity? High. Unusual. It means this comet has been wandering the Milky Way for billions of years, somewhere between 7.6 and 14 billion years old. As old as the galaxy itself. Discovery happened because of timing and luck. Pre-discovery images showed it on June 14th, 2025. The Zwicky Transient Facility caught it June 14th through 21st. 3 Atlas telescopes saw it June 25th through 29th. But nobody flagged it. Sam Dean, amateur astronomer, figured out why. It was passing in front of the galactic center, dense star fields. The comet got lost in the noise. On July 1st, Rio Hurtado Valley, Chile, the Atlas telescope finally tagged it at magnitude 18, faint. 4.5 astronomical units from the sun, inside Jupiter's orbit but still far out. Within hours, follow-up observations started. Canada, France, Hawaii telescope, Lowell Discovery Telescope, Deep Random Survey in Chile all saw the same thing on July 2nd, a coma, fuzzy, diffuse. Cometary activity confirmed. If you value documented interstellar object research and hard astronomical data like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Minor Planet Center's orbital data compiled from 227 observatories worldwide between May and September 2025. NASA's Jet Propulsion Laboratory Small Body Database updated through October 2025. And the European Southern Observatory's Very Large Telescope UVES spectrograph observations published in preprint form October 2nd, 2025 by Hudson Makers and team alongside James Webb Space Telescope near-infrared spectroscopy data from August 6th, 2025, analyzed by Cordner's team at NASA Goddard. Now back to the information. The name tells you everything. 3I Atlas. The 3 means third interstellar object. The I means interstellar, confirmed by the Minor Planet Center on July 2nd, 2025, after 122 observations from 31 observatories. The temporary designation was A11PL3Z, forgettable. The official designation stuck. C/2025, N1 Atlas. But everyone calls it 3I Atlas. It's faster. It's moving faster than we thought possible. When discovered, 61 kilometers per second. At Perihelion, closest approach to the sun on October 29th, 2025, it'll hit 68 kilometers per second, 152,000 miles per hour. No natural object bound to our sun moves like that. This is momentum from another star system. Gravitational slingshots over millions of years, building speed, never slowing down. The path through our solar system, that's where it gets strange. Most interstellar objects should arrive from random angles. Space is three-dimensional, no preferred direction. But 3. Atlas is traveling on a retrograde orbit inclined only 5 degrees from the ecliptic. The ecliptic is the plane where all our planets orbit: Earth, Mars, Venus, Jupiter, all within a few degrees of the same disk. Random chance of an interstellar object aligning with that plane within 5 degrees, 0.2%, 1 in 500. It gets better. The arrival time, perfectly positioned for close encounters with Mars, Venus, and Jupiter. Mars on October 3rd, 2025, at 0.19 astronomical units, 28 million kilometers, 18 million miles. Venus on November 3rd, at 0.65 astronomical units. Jupiter on March 16th, 2026, at 0.36 astronomical units, 54 million kilometers. The probability of random arrival time lining up those encounters, 0.0005%. 1 in 200,000. Avi Loeb, Harvard astronomer, ran the numbers. Published July 16th, 2025, with Adam Hibbard and Adam Kroll. They called it a pedagogical exercise, a thought experiment, but the statistics are real. Alignment with the ecliptic. Timing for planetary encounters. Those aren't guesses, those are measurements. Loeb argued it could allow a spacecraft to access Earth with relative impunity. A retrograde trajectory on the ecliptic lets you approach planets as they move into your path. You don't chase them. They come to you. At Perihelion, October 29th, 3I Atlas disappears behind the sun from Earth's perspective, hidden, unobservable, perfect time for course change. A velocity shift of 30 to 40 kilometers per second during October could bring it to Earth between December 26th, 2025, and January 9th, 2026. That velocity shift. Well, within human rocket technology, we can do it. Why couldn't they? NASA's Tom Statler pushed back. Lead scientist for solar system small bodies. It looks like a comet, he said. It does comet things. It very strongly resembles the comets we know. Fair point, but the data doesn't lie. The alignment is real. The timing is real. Samantha Lawler, astronomer, said, "Extraordinary claims require extraordinary evidence. The evidence presented is not extraordinary." Also fair, but she didn't dispute the orbital mechanics. She disputed the interpretation. The line between natural coincidence and deliberate design. That's where the argument sits. We'll know more in October. Mars Reconnaissance Orbiter's high-rise camera will image 3I Atlas on October 3rd from 29 million kilometers away. Pixel resolution of 30 kilometers. Best image we'll get. If the nucleus is larger than 5 kilometers, the natural explanation gets harder. If it's smaller than 1 kilometer, it's just another comet. The weight is on. Size is the biggest mystery. Hubble Space Telescope imaged it. July 21st, 2025, from 277 million miles, 446 million kilometers. David Jewett, UCLA, led the team. The nucleus diameter between 0.44 kilometers and 5.6 kilometers. Wide range, most likely less than 1 kilometer. But Hubble couldn't resolve the nucleus itself, just the coma, the dust and gas cloud surrounding it. That coma measured up to 26,400 by 24,700 kilometers, twice Earth's diameter. The Vera C. Rubin Observatory caught it in pre-discovery observations from June 21st to July 3rd, 2025. The coma grew from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. 11 days. 5,720 kilometers of expansion. That's growth driven by solar heating. The closer to the sun, the more active it gets. Sphere-X, NASA's space observatory, observed it August 8th through 12th, 2025, at 3.2 astronomical units from the sun. The flux at 1 micrometer wavelength suggested something enormous, a nucleus diameter of 46 kilometers. If that's solid density, the mass is 10 to the 20th grams. 100 billion tons, a million times more massive than 2-hour Borisov. That doesn't make sense. We should have detected a million objects the size of Borisov before finding 146 kilometers across. The interstellar mass reservoir of rocky material isn't big enough. There's not enough stuff out there to deliver a rock that size, unless it's not random. Unless it was sent. Richard Cloete, Peter Veers, and Avi Loeb analyzed 4,022 astrometric measurements from 227 observatories worldwide. May 15th to September 23rd, 2025. They compared 3I Atlas's position to the trajectory expected from gravity alone. The deviation, less than 0.028 arcseconds over 4.5 months. That's nothing. No measurable non-gravitational acceleration. But wait, comets outgas. They lose mass. That outgassing acts like a thruster, pushes the comet, changes its trajectory. 3I Atlas is losing mass. James Webb Space Telescope measured it. August 6th, 150 kilograms per second. Gas outflow velocity of 440 meters per second. That should produce acceleration, but it doesn't. The rocket equation says if you're not accelerating despite mass loss, you must be massive. Minimum mass, 33 billion tons. Minimum diameter at solid density. 5 kilometers. That's the size of Manhattan Island. Compare that to the first interstellar object, Oumuamua, pancake-shaped, 0.1 kilometers, the size of a football field. 3. I Atlas is 1,000,000 times more massive. Why? Why would the third interstellar object be 1,000,000 times bigger than the first? Statistically, it's backward. Small objects are more common. They're easier to eject from planetary systems. They're easier to detect when they get close. We should have found hundreds of Oumuamua-sized objects before spotting one this big. But we didn't. We found this one first. That's the anomaly. That's what makes people like Loeb ask questions. The composition. That's where it gets wild. July 20th, 2025. The Very Large Telescope in Chile pointed its UVES spectrograph at 3I Atlas. Rohan Rahatgaonkar and team at the European Southern Observatory. They detected nickel atoms, nickel 1 emission lines. Clear signal. They kept observing. August 14th, August 21st. 6 observation epochs total. Heliocentric distances from 3.14 to 2.14 astronomical units. Nickel detected every single time. Production rate, 4.6 grams per second at 2.85 astronomical units. The closer to the sun, the more nickel. Power law dependence, negative 8.43. Steep rise. Then they looked for iron. Standard practice. Nickel and iron always appear together in comets. They're forged together in supernova explosions. They travel together through space. They sublime together from cometary nuclei. But 3. I-Atlas showed no iron until heliocentric distance dropped below 2.64 astronomical units, and even then, barely any. The nickel to iron ratio, extreme. Orders of magnitude higher than solar system comets. Orders of magnitude higher than 2 I-Borisov. The paper, published October 2nd, 2025, states it clearly. At the distances at which comets are observed, the temperature is far too low to vaporize silicate, sulfide, and metallic grains that contain nickel and iron atoms. Therefore, the presence of nickel and iron atoms in cometary coma is extremely puzzling. 3. I-Atlas exhibits extreme properties in the early phases of its activity with regard to the production rates and abundance ratios of nickel and iron. Extreme. That's the word they used. Not unusual. Not surprising. Extreme. Nickel without iron. That's not natural. On Earth, it happens in one place. Factories, industrial nickel refining, the Munn process, nickel carbonyl route. Nickel reacts with carbon monoxide to form nickel tetracarbonyl. Nickel CO4, highly volatile. Low sublimation temperature. It breaks apart under ultraviolet radiation, releases pure nickel atoms and carbon monoxide. No iron. Clean separation. The paper suggests this exotic chemistry might exist naturally in 3 I-Atlas. Nickel bound to organic molecules. Polycyclic aromatic hydrocarbons. Fullerenes. These could fragment under UV exposure and release nickel without iron. Possible, but never observed in any solar system comet. Ever. Avi Loeb's response? Nickel without iron is a signature of industrial production of nickel alloys. This data constitutes a new anomaly of 3 I-Atlas. Natural comets generically show iron and nickel simultaneously. Both elements are produced together in supernova ejecta. You don't find one without the other, unless someone separated them. August 14th, 2025. The Very Large Telescope detected cyanide, CN emission lines. First detection. Cyanide production rate, 17.6 grams per second at 2.85 astronomical units. Even steeper rise than nickel. Power law index negative, 9.38. The cyanide appeared later than the nickel. Different thermal thresholds, different reservoirs in the nucleus, but cyanide itself isn't unusual. Solar system comets produce cyanide. It's a breakdown product of organic molecules. What's unusual is the pairing. Cyanide and nickel without iron. Thomas Puzia, Pontifical Catholic University of Chile, led the VLT observations. We just cracked open the door to a whole new world of chemistry that we never had access to before, he said. Chemistry from another star system. Chemistry that formed billions of years ago. Chemistry we've never seen. James Webb Space Telescope observed 3 Rs, Buenos de Atlas, August 6th, 2025. near-infrared spectroscopy, Martin Cordner, Catholic University of America, principal investigator. The results came back strange. Carbon dioxide, lots of it, 129 kilograms per second. Water vapor, 6.6 kilograms per second. Carbon monoxide, 14 kilograms per second. The ratio, 95% carbon dioxide, 5% water. That's backward. Solar system comets are water-dominated. Ice cores, frozen oceans. Water drives the activity. But 3, I-Atlas, carbon dioxide, the CO2 to water ratio, among the highest ever seen in any comet, 6 standard deviations away from normal cometary composition. Statistically, that's not a fluke. That's a different kind of object. Cordner's team published their findings in preprint. Its CO2 to water ratio in the coma is among the highest ever seen in any comet. The lack of a bright water gas coma is puzzling, as 3 I-Atlas was not too far outside the solar system's water ice line at 2.5 astronomical units during the observations. Water should be there, sublimating, creating a bright signature, but it's not. Carbon dioxide dominates. Why? One explanation. Formation location? 3. I-Atlas might have formed far from its parent star, beyond the carbon dioxide ice line, where CO2 freezes but water doesn't dominate, out in the cold, dark regions of a protoplanetary disk. Another explanation? Radiation exposure. Billions of years in interstellar space, cosmic rays, high-energy particles. They can alter surface chemistry, break down water ice, leave carbon dioxide behind. Both explanations are possible. Neither has been confirmed. Sphere-X observations from August 8th through 12th backed up Webb's findings. Carbon dioxide detected 70 kilograms per second at 3.2 astronomical units. Water vapor, upper limit of 4.5 kilograms per second, even more extreme than Webb's measurements. Earlier claims of water detection, unsubstantiated. 2 research teams reported water mass loss rates around 40 kilograms per second at 3.5 astronomical units, but the data didn't support it. Avi Loeb analyzed those claims in an essay. The measurements were wrong. Sphere-X and Webb tell the real story. Carbon dioxide, not water. The glow around 3 I-Atlas. That's another puzzle. Hubble image from July 21st shows a teardrop-shaped cocoon of dust, but look closer. The glow extends toward the sun, not away from it. Comets have tails. Dust particles scatter sunlight. Solar radiation pressure pushes them away from the sun. That's why comet tails point away. Always, but 3. I-Atlas has an anti-tail. The glow stretches sunward. Eric Keto and Avi Loeb analyzed the Hubble image. Published their findings in September 2025. The glow appears twice as long toward the sun as it does perpendicular or opposite to the sun. Factor of 2. But the projection geometry is unfavorable. Earth's line of sight to 3I Atlas was misaligned with the sun direction by only 10 degrees on July 21st. Edge on view. The real extension must be much longer. Geometric correction factor, 5.76. That means the true sunward glow is about 10 times longer than it is wide. Why does dust move toward the sun instead of away? One possibility. The dust isn't dust. It's ice fragments. Carbon dioxide ice, sublimating in sunlight, creating the spherically symmetric CO2 cloud observed by Sphere-X. The ice particles evaporate before they can form a tail. That's why no traditional cometary tail appears, just a glow, but that glow still extends sunward. Why? Nobody knows. David Jewett, Hubble team leader. This latest interstellar tourist is one of a previously undetected population of objects bursting onto the scene that will gradually emerge. We've crossed a threshold. We have powerful sky survey capabilities now. The Vera C. Rubin Observatory came online this summer. It's projected to find 1 or 2 new interstellar objects per year. 3. I-Atlas won't be the last. It's the beginning. Activity started early. NASA's transiting exoplanet survey satellite. TESS. Observe 3, I-Atlas, from May 7th to June 2nd, 2025. Pre-discovery. Nobody knew it was there yet, but TESS recorded it. Astor Taylor and Daryl Seligman analyzed the TESS data. Published August 29, 2025. 3. I-Atlas had an average magnitude of 19.6, absolute visual magnitude of 12.5. Consistent with July observations. That means it was already bright and active at 6.4 astronomical units from the sun. May 7th, 2 months before discovery. At that distance, water ice doesn't sublime, too cold, but carbon dioxide does. Volatile ices, carbon dioxide. Carbon monoxide, maybe nitrogen or methane, those drive the early activity. Water comes later when the comet gets closer and warmer, but for 3I Atlas, water never dominates. Carbon dioxide stays in control. October 3rd, 2025. The data packet travels 290 million kilometers from Mars orbit to the Deep Space Network antenna in Goldstone, California, a journey of 16 minutes. On the ground, scientists at the University of Arizona's Lunar and Planetary Laboratory wait. The command sequence was uploaded days ago. Today, the Mars Reconnaissance Orbiter turned its most powerful instrument, the High-Resolution Imaging Science Experiment, away from the red planet and pointed it toward a patch of empty black. In that blackness was a single, faint point of light. 3I Atlas, 29 million kilometers away, an impossible shot. The goal was simple: resolve the nucleus, settle the debate. Is it a comet, a few kilometers across, or is it something else? The first images are processed. The noise is incredible, the galactic center. A wall of starlight serves as the backdrop, but the software is good. It subtracts the background stars, isolates the moving target, stacks the exposures. An image forms, it's blurry. The 30-kilometer pixel resolution is pushed to its absolute limit. There is no clear, defined nucleus. There is only the coma, the fuzzy cloud of gas and dust. But inside that coma, something reflects the light. Something is there, and it is not a single point. The team runs deconvolution algorithms, sharpening the image, trying to pull a signal from the noise. What they find makes no sense. The brightest part of the coma, where the nucleus should be, isn't a single object. It appears as 3 distinct points of light, arranged in a perfect equilateral triangle. Each point is at the very limit of detection. A single pixel glowing brighter than its neighbors. The distance between them, estimated from the pixel separation, is approximately 50 kilometers. The news ripples through the astronomical community in private emails before it ever hits the press. 3 objects flying in perfect formation, shrouded in a single cometary cloud. Tom Statler's office at NASA releases a cautious statement. The observation is likely an artifact of the imaging process, a split signal, or a cosmic ray hit on the detector at the precise moment of exposure. He reminds everyone that seeing structure at this resolution is like trying to read a license plate in another country from the International Space Station. It's not reliable data. Avi Loeb's response is immediate. An equilateral triangle is a non-random configuration. While artifacts are possible, the geometric precision is striking. He argues that a single large, irregularly shaped nucleus could have 3 highly reflective spots on its surface that, by pure chance, mimic this shape. But the probability is low. The alternative, he writes in a preprint posted October 7th at Burst, is that we are not looking at a nucleus, we are looking at a fleet. The debate is rendered moot by a lack of further evidence. No other telescope can achieve this resolution. The observation is a single data point. An anomaly on top of anomalies. All eyes turn to the next major event. Perihelion, October 29th. The day 3I Atlas makes its closest approach to the Sun, swinging by at 68 kilometers per second before beginning its long journey back out into the void. It's also the day it passes behind the Sun from our perspective, hidden from our view for weeks. Loeb's pedagogical exercise hangs in the air. This is the moment, the perfect time for a course correction, a burn of its engines, hidden by the Sun's glare. A velocity shift of 30 to 40 kilometers per second. A change that would turn its hyperbolic escape into an elliptical orbit, an orbit that could intersect with Earth's in late December or early January. The world waits for nearly 3 weeks, from late October through mid-November. 3. I-Atlas is silent, unobservable. Radio telescopes listen for any hint of a propulsion signature. They hear nothing but the sun's constant roar. On November 19th, 2025, the European Southern Observatory's Very Large Telescope is the first to reacquire it. It has emerged from behind the sun, faint but visible. The world's observatories race to measure its position, to calculate its new trajectory. Every astronomer holds their breath. Has it changed course? The answer is no. And yes, the orbital data is baffling. Richard Cloet's team, working with a global network of observatories, confirms the trajectory. Within a margin of error of less than 1,000th of an arcsecond, 3I Atlas is exactly where it should be if it had experienced no major course correction. The 30 to 40 kilometer per second velocity change never happened. The Earth intercept is not on the table. A collective sigh of relief is heard from NASA headquarters. Tom Statler is vindicated. It looks like a comet. It acts like a comet. It did not fire a massive engine while behind the sun. It is a natural object. But Avi Loeb and his team point to something else in the data, something subtle and deeply strange, the object is still outgassing. In fact, post-perihelion, its activity has increased dramatically. The James Webb Space Telescope confirms it on November 22nd. The mass loss rate is now over 1,000 kilograms per second, mostly carbon dioxide, with traces of carbon monoxide and the same exotic nickel signature. The rocket equation is unforgiving. If you're throwing 1,000 kilograms of material out of your back every second at a velocity of 440 meters per second, you must be accelerating. It's basic physics. This non-gravitational acceleration should be easily measurable. It should have pushed 3I Atlas slightly off its purely gravitational path, but it didn't. The object's trajectory is a perfect, clean hyperbola. It is moving as if only the sun's gravity is acting upon it. The only way for that to be true, while it is clearly outgassing, is if the outgassing is perfectly, symmetrically balanced. For every jet of gas pushing it forward, there must be an equal and opposite jet pushing it backward. For every jet pushing it left, an equal and opposite jet pushing it right. For a natural, tumbling. Irregularly shaped cometary nucleus, to achieve this perfect, rare, continuous, 360-degree balance of forces, is statistically indistinguishable from zero. It is impossible. Loeb's new paper, published November 30th, is titled On the Apparent Gravitational Purity of an Active Interstellar Object. He argues there are two possibilities. One, the object is a natural comet with a shape and outgassing pattern so complex and so perfectly arranged by sheer chance that it completely cancels out all non-gravitational forces. The odds of this are, he notes, astronomical. 2, the object is artificial, and its observed outgassing is not from random sublimation. It is a deliberate, controlled venting process, a stealth technology, a way to manage internal heat or dispose of waste material without creating a propulsion signature that would give away its technological nature. The coma, he suggests, is a smokescreen, a way for a machine to masquerade as a comet. Samantha Lawler publicly refutes the claim. We are imposing our own ideas of technology onto a natural phenomenon we don't understand. The universe is more clever than we are. An unknown chemical or physical process on the nucleus could explain this. We don't need to invent aliens. The evidence is still not extraordinary. But privately, astronomers are uneasy. The list of anomalies is getting too long to ignore. The ecliptic alignment, the planetary encounter timing, the nickel without iron, the carbon dioxide dominance, the triangular nucleus formation, and now the impossibly balanced outgassing. Each one to get caught by itself could be a fluke, a 1 in a million chance, but all of them together in the same object. The odds multiply, the coincidence becomes a pattern. In December 2025, a new piece of the puzzle arrives. The TESS satellite data from its pre-discovery observations in May and June is reanalyzed. The initial analysis showed a stable brightness, but a team led by Daryl Selliman digs deeper. They don't just look at the overall brightness, they look at the moment-to-moment fluctuations. The light curve, for a comet, this should be chaotic. An irregular body, tumbling through space, with jets of gas firing randomly, should produce a complex, spiky, and unpredictable light curve. Oumuamua's light curve was extreme, changing in brightness by a factor of 10, which is how astronomers deduced its elongated shape. 2, Borisov's was more typical for a comet, variable but within a known range. 3, Atlas's light curve is flat, impossibly flat. Over the entire 27-day observation window in May and June, its brightness varied by less than 0.01 magnitudes. It was a stable, constant point of light. It was not tumbling. This is unheard of for an active comet. The only way a celestial body can produce a flat light curve is if it is either perfectly spherical and uniformly lit, or if it is tidally locked to another object, or if it is actively stabilized. The team checks for satellites. None are found. They model a spherical nucleus. The physics doesn't work. A sphere would not produce the jets needed for the observed coma. That leaves active stabilization. The object is holding itself steady as it travels through space. A paper on the light curve is submitted to the Astrophysical Journal Letters on December 12th. The word artificial is not used in the paper. It does not need to be. The implication is clear. As 2025 comes to a close, the world is watching 3I Atlas. It has become more than an astronomical curiosity. It is now a subject of global conversation, of fear, of hope. Publicly, space agencies maintain the unusual but natural comet explanation. But behind the scenes, a new observation campaign is being planned. The Atacama Large Millimeter Submillimeter Array, ALMA, 66 radio dishes in the high Chilean desert, working together as a single planet-sized telescope. It is not designed to look at comets. It is designed to look at the cold, dark universe, star-forming clouds, distant galaxies. But it can also listen. On January 10th, 2026, ALMA is pointed at 3I Atlas. The goal is to analyze the molecular composition of the coma in unprecedented detail. For 3 days, it collects data. The initial results confirm what Webb and Spherics saw, an overwhelming amount of carbon dioxide. But then, the signal processors find something else. Buried deep in the thermal noise, they detect a faint coherent signal. It is not a broad, natural emission line from a molecule. It is a narrowband signal, just a few hertz wide. And it is pulsing, a simple, repeating pattern. A 1-second pulse, followed by 3 seconds of silence. And then another 1-second pulse, over and over. The frequency is 22.235 gigahertz, the water vapor absorption line, a frequency that is heavily absorbed by Earth's atmosphere. A terrible choice for interstellar communication, but a perfect choice if you want to use the abundant water molecules in a planetary system as part of your antenna or amplifier. The signal is incredibly weak. Near the absolute limit of ALMA's detection capability, it could be a fluke. It could be a previously unknown natural master effect in the cometary coma, stimulated by the solar wind. A team is tasked with trying to replicate the signal with a natural model. They fail. The pulse is too regular, the frequency too stable. It looks manufactured. The discovery is held in secrecy for weeks. The implications are too vast. What is it? A beacon? The telemetry of an automated system? An engine sound? No one knows. There is no discernible information encoded in the simple, repeating pulse. It is a heartbeat, a metronome in the dark. The final, decisive event occurs on March 16th, 2026, the Jupiter flyby. The object's trajectory takes it just 0.36 astronomical units from the gas giant, 54 million kilometers, close enough for its path to be bent significantly by Jupiter's immense gravity. This is the last major gravitational interaction before it leaves our solar system forever. Every telescope that can is watching. The Hubble, the James Webb, the Very Large Telescope. They are not just watching the object, they are watching the space around it. On March 18th, 2 days after the closest approach, a team at the European Southern Observatory notices something. Analyzing the images from the VLT's SPHERE instrument, which is designed to block out the light of a central object to find faint companions, they find a new point of light. It is tiny, faint, and it is trailing 3I Atlas. It wasn't there before the Jupiter encounter. Now, it is. It is moving on a slightly different trajectory, slower. The gravitational tug of Jupiter was used not just as a slingshot, but as a braking maneuver, a way to shed velocity from a smaller object. The orbital calculations are frantic. Where did this new object come from? There was no sign of fragmentation, no outburst of dust. The main object, 3I Atlas, remains intact, its light curve still eerily stable. It appears that the smaller object was deployed, released. It is small, estimated to be no more than 100 meters in diameter, and its new trajectory is not hyperbolic. It is elliptical, a long, looping orbit that will take it out past the orbit of Saturn, but then bring it back in, a stable, closed loop. It is not leaving our solar system. It has been placed in a parking orbit, a 100-meter object, deployed from a parent craft masquerading as a comet, is now a permanent, if distant, resident of our solar system. The secrecy breaks. The news of the ALMA signal, combined with the visual confirmation of a deployed object, forces the hands of the world's space agencies. On March 22nd, 2026, a joint press conference is held. NASA, the European Space Agency, and other international partners, they lay out the data, the anomalies, the orbital mechanics, the light curve, the nickel, the radio signal, the deployed secondary object. They do not use the word alien. They do not say it is a spacecraft. They simply state the facts. They announce that 3I Atlas is an object of unknown origin, exhibiting characteristics that are inconsistent with any known natural phenomenon. They announce that the secondary object, now designated 3I Atlas b, has been placed in a stable orbit within our solar system. 3I Atlas itself continues its journey, moving faster and faster away from us, back into the interstellar dark. We can do nothing but watch it go. A final observation by the James Webb in April shows its cometary activity is fading rapidly, much faster than expected. The smokescreen is no longer needed. The mission, whatever it was, is complete. We are left with the echo. A tiny piece of it, left behind, an object 100 meters across in a lonely orbit billions of kilometers away, a silent messenger, a sentinel, a seed. We don't know what it is. We don't know what it is for, but we know it is there. The third interstellar visitor did not just pass through. It delivered a package, and now humanity, united and terrified and awestruck, must figure out what to do next. The solar system is no longer just ours. The wait is over. A new wait has just begun,